Yeah, I think. Shall we start, or do you want to do some introduction or something?
Yes, an introduction. Shall we start? Mohammed Ali sir.
Yeah, we shall start. Yeah.
തുടങ്ങാം അല്ലേ?
അതല്ലേ.
അഖിൽ റെഡി അല്ലേ അഖിൽ? Is it audible? Audible ആണ്.
Yes, audible, ma'am.
Good morning, all of you.
Good morning, madam.
Good morning. Thank you. Respected Principal, Dr. Mohammed Ali sir, our Academic Director, Dr. Sahir sir, Vice Principal, Professor Supi sir, IQAC Coordinator, Mr. Rafiq, my colleagues from Majlis Arts and Science College and faculties from other colleges, and my dear children, a very good morning to all of you. A hearty welcome to this webinar. The webinar is on molecular universe, chemical evolution, and dynamics of interstellar media. Now, in our curriculum, mainly we are studying the chemistry of molecules present on Earth only. That is, molecules present in the land, water, plants, animals, and in atmosphere also to some extent. But the scientists from various countries have explored the nature of many stellar bodies, celestial bodies. And now we know that there is life also there in some stellar bodies. We have concluded to that extent. And our studies of Indian scientists also, the space research is very far ahead when compared to many other countries. So on this context, it is very essential that we should know at least some of the changes taking place in the interstellar medium. We should have an exposure into the chemistry of molecules present in the other bodies, other stellar bodies also, the nature of the molecules, the dynamics, the changes taking place for the molecules, the kinetics of the molecules, and the techniques used for the study. That also should be known to us to some extent. So we should have an exposure to all these terms. And I hope this webinar by Dr. Binu Kumar will give us a peep into the wonderful world of molecular universe. And I would like to say a few words about our resource person, Dr. Binu Kumar. Dr. Binu Kumar has completed his PhD from Planetary and Space Science Research Institute and Rutherford Appleton Laboratory in the United Kingdom. During his PhD, he was awarded the prestigious Marie Curie Fellowship by European Union. His PhD work was primarily on experimental molecular astrophysics employing synchrotron light sources. As part of his research, he has worked in various synchrotron facilities across the globe, namely Diamond Light Source UK, Soleil France, NSS RRC Taiwan, and Astrid Denmark. After completing PhD, he has conducted postdoctoral research employing Diamond Light Source UK. Currently, he is working as a project scientist at the Indian Institute of Astrophysics, Bangalore. His current research interests are laboratory astrochemistry, space instrumentation, high altitude ballooning, and VUV spectroscopy with synchrotron. He has published 16 articles in international reviewed journals and 6 international conference proceedings. And I think we are very lucky to have such a foreign countries. And today's talk will be primarily focused on physics and chemistry of interstellar medium, in particular, evolution, dynamics, and kinetics of matter in between the stars and galaxies will be discussed. In addition to that, the techniques used for understanding and exploring such molecular process will also be explained. So I hope everybody is eagerly waiting for the webinar. I won't take much time. And I invite our principal, Dr. Mohammad Ali sir, for a formal inauguration.
Hello, good morning.
Good morning, sir.
Esteemed resource person, Dr. Binu Kumar, scientist of Indian Institute of Astrophysics, Bangalore, and our beloved head of the Department of Chemistry, Professor Shantakumari Madam, Director of the college, Dr. Safir, Vice Principal, Professor Supi, faculty members of Chemistry Department, and other members of faculty of various colleges, dear student delegates, good morning to you all. At the very outset, I congratulate the department head, Professor Shantakumari Madam, to organize this kind of a program in which we got a resource person who is very unique in a very unique field of science, as you know. The celestial or interstellar space previously occupied in the science fictions only, as we know, in the past. But now, because of the advancement of the science and technology, we know that the scientists have shown through light to the mysterious world. And we are today in a position to explain about the molecular level chemistry and physics, about the happenings of matter in the space between the stars. So this is a marvelous occasion for us to have an idea about what is happening in the energy and matter level in the interstellar space. We are eager to wait and to listen Dr. Binu Kumar so that we will get more insight about the topic, and my dear students and faculty members and me and all the people listening this will get an insight about the space, what is happening there in the molecular level. So once again, congratulations Department of Chemistry, Chandakumari Madam, and all the faculty members who made this event successful. And let me inaugurate this program. I wish good luck to all of you. Thank you. Have a nice day. Jai Hind. Thank you.
Thank you, sir. Now I invite our respected resource person, Dr. Binu Kumar, to start the webinar.
Thank you. Thank you very much for providing this opportunity. Good morning, everyone. So I would like this session to be an interactive one. Hope this is audible to everyone. Is it?
Okay, it's audible.
Yeah, okay, that's great. Thank you very much. So, yeah, thank you very much for providing this opportunity for me. And Professor Muhammad Ali said, I'm also excited to interact with everyone. This is a completely interdisciplinary topic. So, straight away, I will start my presentation. Yeah. So today, when I'm talking about when I say about something like universe or cosmos, or stars or galaxies, then people from the chemistry background, you will think like, okay, what is there in universe or cosmos to discuss about chemistry? I mean, this is all physics, right? Okay. As I told you earlier, I would like this to be something like an interactive session. So anytime when you feel like interrupting me, you can interrupt me. So yeah, yes, I will come back to the presentation. So when I say like universe or cosmos, people think like this is complete astrophysics or this is physics. No, there is a lot of chemistry in universe. So today I will be discussing about this. Say for example, like if you say something about a black hole or a star or a galaxy, a star like our sun, what is there in it? Every one of us know that there is thermonuclear reaction going on there, and this is hydrogen atoms. So then you will ask me like, okay, if you look at some spectra of sun, you will find Fraunhofer lines. There are, absorption lines. All these are like elements, like atomic form. So these are all atoms. So when you say about atoms or something below that, you are discussing physics. But when two atoms join, or when atoms become a molecule, then the chemistry starts. So in according to the latest findings of scientists, the universe is molecular, much more molecular than atomic. So people thought like this is atomic universe. No, it's not. There are molecular features. I mean, in fact, there are plenty of them. And we will be discussing about the chemical evolution and dynamics of this type of interstellar medium. When I say interstellar medium, this is a medium between stars and galaxies. In earlier days, people thought these places were empty. So hope you know, when you talk about empty, empty is not empty. I mean it. That means like when you say vacuum, say for example, you can create a vacuum of 10 to the power of minus 10 millibars or millitors. Being 1 atmosphere, 1021 millibars is our atmospheric pressure. So just imagine 10 to the power of minus 10 millibars. That's that much low pressure. That's the kind of pressure which we feel in interstellar medium. And in those kind of pressures also, there are matter existing there. Of course, yeah, the nature of interactions are very, very, very low. Like, because if a molecule want to meet another molecule, it will take days. So in our, say for example, the fact that when I am talking or when you talk, the molecules move at 330 meters per second. That's the sound, speed of sound, right? There are molecules all around us. So when we talk, it moves at that speed. That means like in fraction of seconds, every molecule is hitting every molecule. But in interstellar medium, it takes days, sometimes even months or years in the time scale to for one molecule to meet the other one. So the physics, chemistry, and astronomy. As I told you, atoms are physics, but molecules are chemistry. So it was told by Arthur Eddington. He was a scientist. He was an atmospheric chemist, atmospheric physicist also. So when they looked at atmosphere, as Professor already Shantakumar already told, we are much more interested in chemistry of matter in Earth. or matter on Earth. Like also we are kind of interested. We have extensively studied comets or meteors, which fall into our atmosphere through our atmosphere. But apart from that, studying about chemistry of a celestial body, that was kind of impossible in up to last decade, up to last century. But this century, because of the technological evolution, we were able to understand much more things in which is happening in our universe elsewhere. So molecular astrophysics, earlier it used to known as molecular astrophysics. Right now a new term has been joined, and that's called astrochemistry. So this is basically chemistry. That's what I wanted to tell you. It's a study of formation and destruction of molecules in the universe and their interactions with radiations and their feedbacks of physics of the environment. This is a completely interdisciplinary topic. It has chemistry in it, it has physics, and it has astronomy. In future, of course, already people have started something called astrobiology. So that's like we are finding out day by day, we are finding out complex molecules, extremely complex ones, like polycyclic aromatic hydrocarbons, chorines, thymine, even uracil has been detected in lab and in lab kind of environment, and they are looking for big amino acids as well as I will come into that in detail. So this is possible through observations from UV to millimeter wave. I hope okay, people from the chemistry background, it will be a little bit difficult to understand about some terms in astronomy. That is like millimeter wave is like it's a radio wave, like you listen to the radio at your home, right? So the same wavelength we can use to observe stars and galaxies in our universe. So also by modeling things like theoretical astrophysics and chemistry, and also laboratory astrochemistry. Actually, that is my expertise field. Like, I was a laboratory astrochemist or even laboratory molecular astrophysics. So yeah, is there any doubt? Anyone has any question? Okay, if there are no questions, I will just go ahead. It's so molecules are found throughout the universe, as I told you, in interstellar clouds. That is like as we see clouds like noctilucent clouds or whatsoever, like rainy clouds, as you say, and all other type of clouds. So there are clouds in interstellar medium as well. So in between stars, there are clouds. Also there are stellar and planetary atmosphere. That's like atmosphere of stars. It's not just sun is a G-type star which has a surface temperature of around 6000 Kelvin. There are stars which are even cooler than sun. So there are very cooler stars, and if there are hotter stars. So there are cooler stars where molecules can stay. So because as I told you, in a star like sun, there won't be, molecules can't exist. It will ionize, we all know. So because of the high radiation field, it will get ionized, and it will reduce to atomic form or even something below that. But in cooler stars, it can molecule can stay as molecule. And in planetary atmosphere, it is not just we have our solar system. There are solar systems outside our galaxies, like not within our galaxy, outside our planetary system. So like there are n number of stars, like 10 to the power of 11 stars in a galaxy, and there are 10 to the power of 11 to 10 to the power of 12 galaxies in the universe. So just imagine how many stars there will be, and each star has planets, and at least one of them will definitely be habitable. Yeah, so I will come to that. But that's like there are several planetary atmospheres. You might have seen popular movies, Hollywood movies like Interstellar and all. The people do time travel, warping, and going to some other planet in some other galaxy, and they have different different type of atmospheres, different timeline, a gravitational force, many things. There are, as a principal told, all these things were science fiction. But now you can, and actually now this is observable. Actually, this is science now. So that's the beauty. So ejecta of evolved stars. So when a star evolves from protostars to its mature stage, there will be an ejecta of stars. There you can find molecules. Then planet forming disk, there you can find molecules. Nuclei of galaxies. Earlier we thought nuclei of galaxies only had black holes, and black hole is something which is holding the complete galaxy. But we found the fingerprints, or we found the evidence of molecules in such kind of environments. And if you look at the typical condition, as I told you, very, very low temperatures and very low pressures. So diffuse clouds, which has a temperature ranging from something like not absolute zero, because that is not possible, as you already know, from few kelvins to 100 kelvins. And the column density, n is the number of molecules per cubic centimeters. That's like kind of 100 molecules per cubic centimeter. For a comparison, I will tell you the column density of air, I mean, just around you is 10 to the power of 16, 10 to the power of 16 per square centimeter. So just imagine 100 per square, I mean, centimeters. So in dense cloud, it is around 10 to the power of 4. And in star forming regions, it's 10 to the power of 6. And protoplanetary disk, that is the disk which is about to form as a planet. So in that areas, you will find a column density of 10 to the power of 8 cubic centimeters. And the temperature will be ranging something from 100 Kelvin to 10 Kelvin. So yeah, so as I told you, like in mean sea level, it's like around 3 into 10 to the power of 19 centimeter cube to something like 1 into 10 to the power of 16 if it is very clean environment without dust or anything like that, and the temperature is around 300 K. So you can understand this is extreme hostile environment, and we think like usually chemistry happens in something like very rich places where the is very less. Then how come chemistry happens in interstellar medium? I'm coming to that story. So interstellar clouds are birthplace of new stars, as I already told you. So evolution abundance of molecules and molecules as a physical diagnosis, because from astrochemistry you can actually draw astrophysics. That means, I mean, you can actually understand. Without astrochemistry you won't be able to understand the dynamics and evolution of a protoplanetary disk or something like that, or and even star forming regions. So this progress strongly driven by technology, as I told you, because of the very latest technologies of interferometry, as well as big and space telescopes. I mean, big ground-based telescopes, as well as space telescope and radio telescopes. That's what drives things. So yeah, this is one of the constellation which is northern hemisphere might have seen this. This is Orion constellation. Hope everyone might have seen this. You see, this is the same image here. This star is called Betelgeuse. So that is a red giant. It's a star you might have studied in +2 classes. Like, I mean, when a star evolved, when the hydrogen is burned out, and when it only comes to helium, it becomes a red star, like red giant. It will become. So our sun will also come to that phase, maybe after like 4.5 billion years or something like that. So then it will expand up to Mars. It will expand. So we will be inside our sun once upon a time, but it will take millions of years. So don't worry, it won't happen right now. Right now we are already under the pressure of COVID-19. We have enough things to worry. So being sun being a red giant is something that you don't have to worry about. So my point is, so this is one of the constellation you can see on every day. Like if you look up, if it is not a cloudy day, you will find these stars, at least these 4 stars, if your eyesight is very good. So these 4 stars. So this is the belt of the hunter, though this is called hunter. So or Orion. So this is a head of the hunter. These are shoulders. This is a belt. This is here this is a sword which is hanging from the belt. So this is there in almost all mythology. This is a mythological concept. So here, if you see, there is a light brightness you will see. That's a interstellar cloud actually. So that's what I am coming to. So there you will find this light you see here. That is this photo. This is like, I mean, this is zoomed in type. This is called Horsehead Nebula. If you look at this area, you see something like a head of a horse. So actually that's not a horse head. It's dust, as well as it's a dense matter over there. So the dense cloud there is actually blocking the light behind that. So there are stars behind that. that is actually blocking the light. So that is a molecular cloud. I was talking about molecular cloud. That means that cloud has a lot of molecules, I mean simple as well as complex molecules, and that's actually it's not seen, you can't see that by naked eyes. If you go to very clear sky, you can see that patch of sky there, but like, I mean, to see something like this you need a telescope. So this is a combined image, it's not just a visible image. That means like it's not, you won't be able to directly take a photograph and zoom it and find out something like this. This is like a false image. That's like the observation was done in millimeter, that's infrared, and then also in things also in visible region. So yeah, so here if you see, you will find a brightness here, that's the reflection nebulae. It's called NGC 2023. And if you see, like, I mean, as I told you earlier, there are, like, I mean, okay, these things, especially these type of galaxies or stars, whatever you find, this is in past. Like, I mean, you won't be able to see anything which is in present, because the nearest star which you see on a normal day is 4 light years away, the Proxima Centauri. So, like, I mean, that means it will take 4.5 years for that light to travel from that star to your eye to detect that. That means that star was standing there 4.5 years ago. Right now, you don't know where it is. And like that, if you see this Horsehead Nebula or even the Orion constellation, that is 1,375 light years. That's like it was there before 1,375 years. Today we don't know where it is. So whatever we observe in our universe, everything is in past. So we are looking at past of our that's the reason why in news you might have I mean, you will come across points like, okay, astronomers have find something from Big Bang, back from Big Bang, or they found something which is very old galaxy or high redshift or something like that. That means there are photons which are still traveling from the very center of the Big Bang. Hope everyone heard about Big Bang. I mean, that's the most acceptable theory about formation of universe. So from the Big Bang, the photons are still traveling. Sometimes it comes and falls on our telescopes or instruments, and that's how we find how these things evolved and how the dynamics of universe changed. So this is a typical astrophysical. Okay, everyone as being chemist or even physicist, we all know this periodic table of elements. So if you look at different color codes, so these are, like, I mean, big blue colors. These directly came from Big Bang. Like, I mean, we know right after 4 seconds of Big Bang, there are like gluon plasma. There was quark and gluon plasma. Then quark gluon plasma combined to form um, neutrinos, and then also like a upper quark, down quark, then it formed protons, neutrons, then it formed molecules, I mean, sorry, atoms, then thereon it formed molecules as well. So like these are the elements which were formed during Big Bang. And if you see the other elements, like if you see carbon, nitrogen, oxygen, fluorine, neon, and all these, I mean, partially green as well as supernovae. Supernovae is one of the final stages of stars. When a star explodes, that's when it is supernovae. And large star, very high mass stars, they formed all these type of, because when you burn hydrogen, you get helium. When you burn helium, burn in the sense it's thermonuclear reaction, fusion reaction to be precise. I mean, when you fuse it, it forms carbon from, then as a cycle there are nitrogen, oxygen, fluorine, and so on. Also, so if you look at the other elements, majority of these elements are formed in supernovae. That means when a star, majority of these elements form, and these are man-made, and these are from stars, and even beryllium and boron, these elements form through. So lithium is very important right now, everyone knows, because of the batteries. So that is very rare, one of the rarest elements, and this didn't form during Big Bang. It was formed using cosmic rays. So this is how the elements formed. So now we know how, I mean, I'm going to explain. So this is how a chemist look at its chemistry, a person look at its periodic table, but this is how an astronomer's periodic table look like, because they are looking at abundance of the elements. Because if you look at hydrogen, like hydrogen as 1, the abundance of hydrogen, keep it as normalcy like 1, then helium will be like 0.1. That's like 10% of hydrogen what is present in our universe. That is what is present in the helium amount of helium is like 0.1, only 10%. If you look at carbon, nitrogen, oxygen and all, it's like 4, 1 or 6 into 10 to the power of -4. And neon is will be, these size of the dots show the amount, actually the amount, abundance of those things: magnesium, iron, silicon, sulfur, argon. These are like trace, extremely trace elements. So this is the cosmic abundance, which is given here in another table. So these are like also like whether it is a molecule or inert, or whether which is present in which form, like which is helium is as an inert gas or a noble gas. So oxygen, most of the oxygen is trapped in carbon monoxide, and even most of the carbon is also trapped as carbon monoxide, and nitrogen as nitrogen molecule, and neon as an inert one, silicon, magnesium, and iron in the form of dust. So yeah, so some of the key facts like hydrogen fact, the amount of abundance of hydrogen is 1,000 times larger than any other elements, as I showed you. And hydrogen and nitrogen and CO, all these things like carbon, hydrogen, nitrogen and oxygen, the key and vital elements which is needed for life, formation of life, this is locked in the form of molecules. So this is chemistry. So as I told from the beginning, so this is where the chemistry comes in. If this is like atoms, that doesn't have much chemistry there, but it's physics. Now the chemistry comes. So if the hydrogen and the amount of hydrogen atom is more than oxygen, that is a reducing environment. And you know that when the oxygen atom availability is high, that's an oxidizing environment. So there are several different ways in which chemistry occurs in the interstellar materials. That's through a gas-phase chemistry, because we know that in that kind of environment, most of the gas, most of the elements are in gas phase, especially the molecules H2, N2, and Cu, all are gas, and the rest of the silicon, magnesium, as well as iron, which I told you, is in dust form. That's like solid form. But these majority of these abundant elements are in gas form. So gas phase chemistry is there. Then grain surface chemistry. That's like there are dust grains or silicon or carbonaceous one. And onto that, because of the very low temperature, 100 Kelvin, you know what, the liquid nitrogen temperature is 77 K. You might have seen liquid nitrogen. So this kind of in that range, 100 Kelvin temperature. So anything can ooze out. Like, there will be physics option onto anything which is flying around will definitely stick onto a grain at that temperature. And other processes like energetic processing of these ices, like when grain surface forms ices, and if those ices were processed by energetic processing like UV, electron, cosmic ray, and shock. So that's how the chemistry starts. So there are unique probes, like you can look at, so the molecules, why they are very important, because as I told you, without astrochemistry you won't be able to study much astrophysics, because these molecules are unique probes, and they can give us the density of that particular region. If you understand the T, like a background temperature of those molecules from vibrational spectroscopy. I'm coming to that tools which we use. And so from that, you will be able to understand the density of that region. You can understand the ionization rate of that region. From that, you will be able to understand much of physics in that region, like the energy level and things like that. So these are also unique props of kinematics and chemical composition as well as evolution. If you look at the chemical composition of a particular region, you will understand how this has been evolved, because we can formulate some computational chemistry like networks, and from that you can extrapolate and find out how this we won't be able to test this because the time scale which we have in astronomical processes are very huge, like millions of years or billions of years. So you can't wait in your lab for 1 million years for a chemistry experiment to happen, right? So what we have to do, we have to simulate some computational process, and we can simulate 1 million years or 1 giga years or whatever at very high time spatial scales, and then you will be able to find out how these things evolve in nature. And it is a coolant of gas, like molecules which when hit on another molecule will take up the energy, extra energy, and that's how the molecules will come down to, if you want a molecule, sorry, a atom to become a molecule, then the extra energy should be pumped out or it should be released. I will in detail I will tell you the processes and the collision time. As I told you, if one molecule want to go and hit another molecule, the meeting time, it will take almost 1 month at 10 Kelvin for this molecular density, that is 10 to the power of 4 cubic centimeters. That means there are 10 to the power of 4, that's 10,000 atoms in 1 cubic centimeter, but still it will take 1 month at 10 Kelvin. That's the time frame it will take. So the chemical time is like 10 to the power of 4 to 10 to the power of 5 years in molecular cloud. So to form something like that, this much time it will take. So it is not possible for somebody to simulate something in the lab, actual simulation, but computational simulation it is possible. So lifetime of a cloud is like 10 to the power of 6 years, and during low mass star formation it is 10 to the power of 6. That we precisely say that because in high mass star formation is very short time scale. It happens very fast, because if the star is heavy, the reaction rate is very heavy, very fast. Chemistry is slow, yet there are many molecules in the interstellar medium. So how they form? So okay, so I'm just skipping few slides because I think I'm running a bit slow. So so as I told you, there until now, till date, there are around 210 molecules. 218 molecules has been detected. Out of that, 170 in interstellar and circumstellar molecules, 41 extragalactic molecules, up to 2 atoms or something like that, and 20 positive ions has been cation has been detected, and 6 negative ions has been detected, and 30 free radical, 20 isomers, 6 linear and 6 cyclic species like polycyclic aromatic hydrocarbons, you all know that the benzene ring, or even silicon, something molecules which is silicon of silicon oxides or something like that, higher oxides of silicon, phosphorus, chlorine, and things like that. So if you look at the last line, you will understand the actual importance, because organic molecules like ethers, acids, alcohols, aldehydes, and all other higher molecules, even like nucleic acids, amino acid bases has been already been detected. So this is a list of few molecules. I have taken this from a database called clone database. You can go to, I hope these slides are available online. So if you would like to go and explore a little more, you can go to the website and you will find till date, until April, 218 molecules has been detected, and you see the complexity of molecules. You see these type of molecules still exist and they stay in interstellar medium, in despite of the fact that the environment is harsh and there are a lot of lot of energetic processing, as well as very high shocks which is being happening. But so this is actually showing us how the life started, or I'm not talking about intelligent life, at least life, particle which can give life, something like nucleobases or something like that. So we are slowly finding out. So we started with very simple molecules. Now we are going to complex molecules. People have already identified bucky balls, like C60s, everything in nature. So especially in interstellar medium. So yes, we are coming to that answering. We are maybe in few years, maybe in 20 years, we may come to know from where the life came, whether it is originated in Earth or it came from somewhere outside or whatsoever. So the physical conditions, I already told you, the diffuse clouds. We saw a dense cloud, that is the Horsehead Nebula. I have shown you a dense cloud which is blocking the light behind and which looks like a horse head, and which is in a constellation which is available, which is visible by your naked eye. And you can tonight itself, if possible, you can go out and see you will find the Orion Nebula, and Betelgeuse is always there. Like, I mean, you can easily identify the red star in that Orion constellation. And also, if I mean, if you are astronomy enthusiast, at least by chance, if you would like to see something, there is some one one of the important comets, an interstellar comet, which is being visible. So it's called Neowise comet. Hope you might have seen in some media bites somewhere here and there. So this is a comet which came from outside our solar system. So right now it is visible by naked eye. When on 22nd it was closest to Earth, but still it is visible. So early morning around like 4:30 or 5, if you wake up at that time, you can just go out and see in the west direction. You may possibly be able to see a comet. So it has it has a tail, long tail, and you will be definitely be able to find it out. Or else, if you nowadays it is easy because you don't have to be astronomer. You can install apps which help you to find out celestial bodies. I recommend Sky Map. I think it is by Google itself. So if you like, if you have Google Map, you can install Sky Map. So and just switch on your data, show to the sky. You will find I mean, it's fantastic. It will identify all the stars, galaxies, whatever which is visible to your naked eye. So by that you will be able to identify this Neowise comet. So I hope you will be able to. Even that comet has organic molecules in its tail. My point is, like, the tail which is behind the comet, that has a lot of ice. I mean, very cold molecule in that, and there are a lot of organic molecules you will find in that kind of cometary particles. So there are several places where you find it: comets, a planetary atmosphere, protoplanetary disk. Protoplanetary disk is something from which a planet forms. Before the planet forms, it's all rocky particle in a planetary disk. Then it combines and it forms a planet. So that is from a planetary disk. Hot cores are cores which is being about to collapse as a star. I will explain you this in detail with some beautiful pictures. And yeah, dense clouds. I already showed you a dense cloud, and there are diffuse clouds. There were like NGC 2023. I have shown you reflection galaxy in that picture. That's a diffuse cloud. So look at this picture. So this is a photo of a sky. I mean, just a patch of sky. So if you look in the center, you think, okay, nothing is there. So it's black, it's dark. There's nothing there. Actually, that is not the case. That's a dark cloud. It's a very thick cloud there. So it's like analogous to a dark day, a dark monsoon day on your, on Earth. It's like you won't be able to see the sun, and you feel like, okay, this is very dark day. So the same thing happens here. There is a very thick molecular cloud in between us in the line of sight and those stars. That's the reason why this. But we will be. But we are looking here. There is a limitation. There is an observational bias. That's like we are looking in something. This is a visible spectrum. I mean, visible image. That means we are looking at with our naked eye. So then we won't be able to see that stars behind this cloud. But if you look very close, you see these red dots there. These are all stars behind, and behind that cloud only little amount of light is being pierced through those dark cloud. But if you look in some other wavelength, like millimeter wave, as I told you, the radio waves, or infrared wave, or some other medium, like, I mean, some other electromagnetic radiation field, then you will be able to detect those stars. My point is, like, there are several different techniques. So astrochemistry is a very vibrant as well as interdisciplinary technique. You may think like, okay, what a chemist can do here. There are a lot of things a chemist can do. As I told you, all the chemical pathways which is being, I mean, we know astronomers observe it in the sky, but they don't know how these molecules formed there. Then they have to go to a chemist to understand how these things formed there and how the evolution happened. So those those gaps, or those dots, you should connect that. I mean, the chemist should connect that. Definitely a physicist don't have the enough expertise or experience to do that. So this is a life cycle. In brief, this is a life cycle of a galaxy or even a stars. Like, I mean, there will be a diffuse cloud, then it will collapse under its gravity. You know that when it collapses under its gravity, once it reaches like an equilibrium stage, when the pressure, heat pressure from the gas and the gravitational collapse balances, then it will disintegrate. Then it forms a accretion disk, and during accretion disk there are several stars formed in the star formation regions, and these disks these are called protoplanetary disk, where the planets form and the center core will become a star. And once the stars dies, there will be mass loss, and this when it explodes, okay, if it crosses the 1.4 Chandrasekhar limit, it goes to a different life cycle. If it is below that, it after the red giant cycle, it follows a different path. Hope you know about all these things. So then I don't have enough time to explain all these astrophysics, but I am only focusing on the chemistry on this. So like if you look at, okay, this is what I was talking about. There is a comet, like, I mean, if you see this, so okay, this picture, this is a cartoon of a comet. So you see a comet coming in, meteorites. So all these rocky particles, which is there after in the accretion disk, the belt between Mars and Jupiter, or in the Kuiper belt, in Oort cloud, anywhere. So those things will fly in, and those forms asteroids or comets. So if you look at the actual quantitative way, like, I mean, we were talking all qualitative things, right? I mean, in between I gave you some numbers, but still it was all qualitative. But if you look at the quantitative way, this is based on the number of hydrogen atoms per centimeter square. How many, I mean, the density compared to number of hydrogen atoms. You see the scale, it's like in the scale of 2 into 10 to the power of 19 to 8 into 10 to the power of 29. So in the diffuse atomic region, it is like the density is very less, especially for the hydrogen as well as helium. Hydrogen molecule is this hydrogen molecule, then this when it diffuse molecular as well as dense molecular cloud, the hydrogen atoms slowly they form into hydrogen molecule. So you see that the number of hydrogen molecule are high here, and the number of hydrogen atoms comes down here. So that means like when it is goes from diffuse to dense molecular cloud, the formation of like also here, if you see that in the diffuse atom, and I mean photodissociated regions, you will find ions of carbons and as well as electrons, free electrons flying around. Then they becomes carbon atoms, and then it forms, I mean, joins with carbon oxygen molecules, and it gets trapped in carbon monoxide. So as I told you, hydrogen, carbon monoxide, nitrogen, I mean, molecule, these are the primary molecules which form inside a dense molecular cloud. Then later on they accrete together and they form dense clouds. This is the same picture which I have showed you earlier. This is in actual orientation. So this is the sword which I showed you. Here is the dense molecular cloud here. Yeah, is there any doubt or any question so far?
Akhil.
Hello.
Hello. Akhil. Akhil. There are any questions in the YouTube?
Is there any questions or doubts?
Please.
Okay, all right. Otherwise, what I can do is like you can collate all those questions, and I can explain it later, I think. Is that okay? Yeah, yes, please.
How the galaxy maintains its equilibrium? That was the question. From Mubashira Faiz.
Okay.
How the galaxy maintains its equilibrium?
Equilibrium in the sense chemical equilibrium or physical equilibrium. Physically, it is because of the gravitation, the balancing of gravitational as well as radiation pressure. The radiation pressure, which is pushing as well as giving a stable position for each and every stars, as well as if you look at a galaxy like ours, like Milky Way. So it's a spiral galaxy. It has a disk in the center. You see the bulge in the center. And if you look at sky, normal sky, you will find the disk. That is the protoplanetary. Sorry, that is the dust accumulation in the center of the galaxy. That's the central dust disk, which is being seen. So if you look at the galactic bulge, it is in that position because it was maintained by its angular momentum. So also, plus if you see microscopically, then I will have to explain each and every feature, like whether it's a spiral arm, in the spiral arm where the star formation happens, how the balancing happens, how the equilibrium is being maintained, or as a whole, it's because of radiation pressure plus the gravitational force acting against it. So usually people think, according to the popular accepted theories, most of the galaxies have a black hole in the center of it, in its center, and that's how the gravity being maintained. Is that answer the question? Yeah, if you have any other thing to raise, you can put this up during the discussion session. So I was just meaning, like, okay, if you have any doubt in the slides, then you can ask me. Otherwise, if you have a general doubt or something like that, you can just post it in the chat box, and we can have a discussion during the break. Yeah, so yeah, I will just move on. So this is another molecular cloud called Taurus, and you can also find the same constellation on the sky. And this is also an optical plus near infrared image which is being combined. So these interstellar cloud bands, you see, these are actually imaged in near IR. Near IR, okay, majority of you might be using spectroscopy as a tool in your lab, so you might be knowing near IR, mid IR, as well as far IR. So it's a near IR image. These bands, these, like, cloud kind of thing, this is being imaged in near IR, and the optical, these stars are in the optical band. So this is a combined image. You won't see this type of image when you take a one, if you observe in optical or near IR, it's combined. So usually whenever you see an image, especially astronomical image, you please keep it in mind that that's not a proper image. It's like a false image. We build it, like we use something like Photoshop. There are different softwares which is being used that is very precise and scientific, which has astrometry and a photometry in it. So like we use that to create this type of images, but these are not like some actual photograph which we take in one single wavelength band, or few in optical band or something like that. So as I told you, I was talking about diffuse interstellar medium, cold dense matter, photodissociated region, and all. In addition to that, there are complex molecules, organic molecules that has been detected in something called comets, or even asteroids, or as meteorites. So these are meteorites that you might be seeing. In Malayalam we call it Ulka or something like that, even like shooting stars, so in common name. So these fall, you will find recently there in news there was an article saying, like, somebody find a big chunk of 30-kilogram meteorite in Germany, which was just lying in his garden. So like recently only he came to know that it was a meteorite, and it's very expensive, and it's like, it's a very rare piece of metal. It's not just piece of metal, it's something which came from outside our earth. So 200 plus, more than 200 amino acids has already been detected inside such things like meteorites, including adenine, guanine, and uracil. All these nucleobases as well as fatty acid has also been detected. So I was talking about how it forms, how the diffuse environment look like, and what's all those parameters, how we encountered these parameters. That is through observation. So astrochemistry is a multi-field approach. So through observation, that is through infrared, radio, visual, X-rays, and UV, and we are like observing. We are observing our universe, and we are finding it out. And the other things, like an actual output of an astrochemistry that can be brought in through models, modeling early universe, interstellar clouds, star forming regions, planetary atmospheres. And also we do experiments in the laboratory, that is through spectroscopy. If an astronomer is observing in infrared spectroscopy, if he is recording an infrared spectra of a diffuse gas cloud, he has to know the transition bands, right? He has to know if he know if he want to understand, okay, what is happening there, then he need oscillator strength. So that oscillator strength can be calculated, and I mean it can be measured from a laboratory spectra, and from that he can take an input, then he can build it upon that. Then the collision rate that can be calculated from sputtering as well as collision experiments. Then reaction rates can also be measured at laboratory. Now with the help of attosecond lasers and nanosecond lasers, we will be able to measure any type of reaction rates. And grain surface processes, like process on surface of a grain with an ice coating on it, we will be able to do energetic processing, and we will be able to do that. So actually my expertise is laboratory astrochemistry, or you can call laboratory molecular astrophysics. So I build instruments. I don't do observation or modeling, but I build instruments for astronomers to observe at stars or galaxies, or I build instruments for people who do experiments in the lab for doing different, getting different kinetics. So I'm just going, I think I'm running a bit slow, so just going a bit fast. So detecting molecules, as I told you, we use spectroscopy as a tool at different wavelengths. So absorption in UV, optical, or IR, or emission in millimeters, or gas phase as well as ISIS. So if you look at a continuous spectrum, you see, like, I mean, if you look at a incandescent lamp through a prism, you know that you will get a continuous spectrum. If you have a hot gas there, you will get like emission lines. If you have a cold gas in between the source as well as your eye or observing medium, so then you get absorption lines. So usually you look absorption lines, UV, optical, and IR. There are stars which emit in extreme soft X-rays and extreme UVs as well as UV. Keep those stars, and we can model them, and also we will fit those models onto the observed spectra, and you can baseline fit it, and you will be able to understand what is the quantum density of a particular star in this cold gas, or the abundance, or how fast it is moving, what's the temperature. All those data can be reduced from those type of absorption or emission lines. So detecting molecules, as already told you, like we can observe anything from X-rays to millimeter waves. So in X-rays, you saw in the center of the galaxy, as somebody already asked a question about the galaxy. So in a galaxy, say for example, if you are observing a galaxy in different wavelength regions, like if you look at X-rays, you see the active galactic nuclei, or the AGN areas, the very center from where the hard X-rays as well as soft X-rays being emitted. So if you look in ultraviolet, you will see this type of all the bands, like all spiral lamps where the stars are forming, the very young stars form. If you look at visible light, you will find again the dust plus complete scattering and all the visible emission from middle-aged stars like sun and things like that. If you look at infrared, the actual dust, complete dust emission, you will be able to see. Then rest of the cold gas as well as other accretory things, you will be able to see in millimeter as well as radio waves. So this is how we look at different a single galaxy. You can look at different wavelength regions, and you can understand different dynamics, because all these images belongs to a single galaxy, like one of our Milky Way, a type of galaxy, a spiral galaxy. And you see that in different images you will find you can infer different things. So rotational, because of okay, you are all using like microwave at your home. So you see in between the infrared and millimeter, that is microwave region there. So you get a rotation spectra from that. You have a vibrational spectra again from the rotational from the radio waves, and vibration from the millimeter, or from the microwave. Then electronic transition, that is being in visible as well as ultraviolet, and the combined ones. So but there are limitations, as I told you. From ground you won't be able to see ultraviolet, as well as something which is above this you won't be able to see. And even infrared, only few bands are being observed on the ground. But millimeter and radio waves, yes, we will be able to observe from our ground. So rest of the things you have to build satellites. Like actually, I am working on a project on which we will be sending a satellite, a spectrometer, which is being on board on a satellite, and it will be observing. At the moment, we have one dedicated satellite, AstroSat, that is in the orbit. In that UVIT, the ultraviolet telescope, was built by my institute, Indian Institute of Astrophysics. I mean, engineers and scientists there built it. So that is being looking in the ultraviolet region of the sky. You see something like this. The ultraviolet UVIT telescope on board AstroSat can take pictures like this, and it can send us, pictures like this. So detecting molecules in the same story which I was talking about, but it's in detail. Like, I mean, if it's a meter wave or a millimeter wave, that gives the rotational, and this is the vibrational spectra, or both combined raw vibrational spectra can also be inferred. Then there is UV visible spectra because of the electron distribution, as also like, I mean, soft X-rays. Then gamma ray spectra, nuclear magnetic resonance, as well as those kind of nuclear configuration, in change in the nuclear configuration, emits a gamma ray, and you will be able to understand all the dynamics, chemical dynamics, by observing at different wavelengths. Hope, I mean, you might have already studied these things in quantum chemistry or even spectroscopy. So this is a combined thing. Like, I mean, the combined energy will be electronic vibration and rotation. Rotation, vibration, and electronic transitions are the most and vital, fingerprints, or they will provide us the insight about the diffuse clouds as well as things. So when you look at, it's the same thing which I have shown you using that bulb, that analogy. The same thing, star is there, and in the line of sight we have clouds. So you ask, okay, all these clouds are not there in the line of sight. Yeah, absolutely. You won't be able to see, or you won't be able to, model or get a spectra unless and until there is a star behind that. So if there are like parent stars, or there are stars, or like, I mean, a source of light which is being there, otherwise we won't be able to get any absorption spectra. Then you will have to look at another bands like millimeter or meter wave bands to look at the cloud. So this is a background, continuum light. And here you will find, interstellar lines. These are the absorption lines. In the intensity, there is a dip in the intensity, which is because of the absorption here. You all know about the Beer-Lambert's law, right? So it's basically the Beer-Lambert's law. So in the diffuse, I'm not getting into details. So it's like how the magnitude, these are all astronomical terms, 0.3 magnitude, visible magnitude, how it is, and how much hydrogen atom being there, and how it is being molecular, or those kind of calculation, how we can find out these things. If you are interested in doing research or something more in this, you can directly contact me, or I can provide you some databases where you can find some actual data, and you can process it using IRAF or any spectroscopy spectral tool, and you will be directly able to reduce a spectra of a cold molecular cloud or dark cloud. So right now, I mean, there are so many databases which is being available online free. These are free data which is lying there, and anybody can go out and observe it. Even there is a radio telescope in India that is one of the best telescopes. It's in Goddard near in Pune. That's under the control of National Center for Radio Astronomy, NCRA. So National Center for Radio Astronomy website, if you go and visit, you will find these type of databases there. And also there is a workshop called RAD at Home, Radio Astronomy at doorstep. So you will be able to reduce your own data, your own things, and infer something out of that. So molecular spectroscopy is the basic thing, one of the basic tools which we use to identify these molecular species there, electronic transition, vibrational transitions, rotational transition, and small splitting in the radio waves. So these type of transition which use, hope everyone knows these kind of things from your spectroscopy course itself. So look at your molecular spectra, and you have to model a background star. That is basically a black body radiation curve. If you know the background, if you know the surface temperature of that particular star, you can computationally create a black body radiation curve and fit it onto your molecular spectra, reduce it, and there it there it is. I mean, when I say it is easy, but it's really tricky, and I will show you a spectra how it looks like. It has a lot of lines. I mean, it's a forest of lines. Finding out lines out of that is really tricky, and definitely it takes a lot of time for processing. So the concept is easy. This is basic physics as well as chemistry, but when you employ it, this is kind of really getting complicated. So there is another thing. As I okay, now I was always talking about interstellar gas, how the gas blocks and how it is giving you a absorption or emission spectra, or how we can identify it, where we have to look and how we have to look. But I'm talking about something else that's called interstellar dust. As I told you when I showed you that galaxy, the life cycle of galaxy, definitely after the collapse of a star or a galaxy, in a galaxy there will be a lot of dust which is being formed, which is form of silicate, carbonaceous, or even iron or magnesium, those kind of materials. And onto that, those are solid particles, and which is being of the size of 0.1 microns. And yeah, abundance of which has an abundance of 1%, 10 to the power of minus 12 by number. So silicon, iron, magnesium, and carbonaceous part. The carbonaceous part is more than the oxygenated part, that's 60 to 30 in percentage, and the 10% is rust of the matter. And so these kind of interstellar dust play a very vital role in formation of molecules. How? That's by giving, I mean, that's because if you look at this, okay, this is again how we find out the solid phase, but I will just tell you how it's being formed. Like, I mean, onto a dust, just imagine if there is a dust particle onto that at very low temperature, like 10 to 100 Kelvin, and the molecules will freeze onto that, and the molecule will stay onto that molecules and release the extra energy. As you know, when a atom which is being flying around, when it comes and bumps on a dust particle, it will release its extra energy, right? And it will stay on there, it will rest there until a second atom will come and it meets the second particle, like, I mean, the particle which is already on the dust, and then it forms, if there is enough energy as well as enough conditions, then it forms a molecule. That's how majority of the molecules, I mean, especially the complex organic molecules in the interstellar medium formed. So these are ices in the sense, it's not a water ice. I'm telling you, at very low temperature, ammonia, even like, I mean, methane, anything can be, like at 10 Kelvin, everything is ice, right? So whatever which is being physics solved, I mean, chemistry option as a physics option. Once the physics option is there, then after the processing, energetic processing, that can be chemistry solved onto the same surface itself, and it can stay there. So this is how we look at it. So if it's a cold dust ice mantles, then we will be able to see on the continuum line, we will be able to see the dips. And these type of dips, from that we understand that these are called dust matters. I mean, and these are not like gas molecules, because looking at the shape as well as the intensity of the curves, we will be able to understand from the flux versus the wavelength. We will be able to understand whether it is ice, like, I mean, ice, or like whether it is a solid phase molecule or is it a gas phase molecule. So there are lot of evidences. Now there are a lot of evidences. Basically, we use the Spitzer telescope data, which is also a public. Anybody can just go ahead. Anybody who know basic molecular chemistry can go ahead and do research in that. It's readily available online over there. So yeah, so like they found water ices. Like if you look at the wavelength versus the flux data here, basically this is in millimeter wavelength. You will see the silicate absorption over here, and methanol ice over here, and water ice, and carbon dioxide dip over here. This is actually in the mid infrared. So the complete, if you see the microwave area of this, especially these are from the tau as well as IRS region of this called dark matter. You see a dark thing here. This is the accretion disk which I was talking about. I'll tell you in detail. So this is what is being found. So in the opaque, in optical as well as UV, then it is because of it's shielded from the associated region. So in that case, you can look at millimeter wave emissions or mid-infrared wave emissions from rotational transition as well as vibrational transition. So you basically, when you look at millimeter wave, you find H2 and CH4 molecules, and also you will be able to look in, if you look at mid-infrared absorption, you will be able to find very complex molecules. I mean, whatever alcohol, aldehydes, and other amino acids as well. So even in Earth atmospheres, we have a lot of molecules. You know, we have a lot of water, O2, CO2. All these absorb in these areas. So that's the reason why I told you from ground there is a lot of limitation. The constraints are more here from the ground, but still we looking at millimeter wave. So this is a UV spectroscopy. So this was one of the first finding from which we found the cyanide molecule in 3874.6. So as well as CH molecule from the stellar lines, stellar helium lines. They in 1930, 1940 time. This is like kind of history of astrochemistry. At that time itself, they found it in the line of sight, the visible region itself, electronic transitions. But later on, because of the technological advancement, we were able to find out other things, like, I mean, all other lines in the, these are all like visible as well as UV lines. You can see this is in Armstrong 3880. So these are lines which were, at that time, these were like suspected lines. They were thinking whether is it cyanide or is it CH molecule or CH ion or something like that. But okay, in 1937, they found CH, as well as in 1940, they found McKellar found cyanide molecules using this visible UV spectra. Then later on, when they found the diffuse interstellar bands, like diffuse band with a lot of forest of lines, absorption lines in this, then they started looking at different other wavelengths like IR. So from IR, they found so many raw vibrational transitions, and from that, they were able to find out large gas phase molecules and very large carbon atoms. So yeah, again, these are different type of uh, facilities. As I told you, split serve, we have Keck 1 and 2. There are several other radio telescopes, including NCRA radio telescopes in our Pune itself, and also there are millimeter telescopes. There are very large telescopes. So this is one of the surveys by IRAM, Orion KL survey. So you look at the lines, like this is what I was telling about. If you look in these regions, this is in frequency. Don't confuse it with wavelength, because physicists are more kind of, more kind of accustomed with frequency than wavelength. I know you might be expressing everything in lambda, like wave numbers, or even wavelength, but we usually used to express it in frequency. Please forgive me for that notation. But like, I mean, the main content was, this is how a interstellar spectra will look like. I mean, there will be forest of lines. You will find a lot of transitions. You will have to identify which one is that, and you will find a lot of molecules with C, and then like nitrogen cyanide molecules. And so yeah, this is antenna temperature. Basically, this is a millimeter wave observation. That's why you find all these transitions. So yeah, there are a lot of lines which you will find here. So these are both same. So yeah, I don't have enough time to explain the complete thing. So the Orion Nebula, which I showed you earlier, the Horsehead Nebula is in that region. In above the belt, there is another region where the Horsehead is a different one. The Horsehead is below this, and this is just above that. You will find oxygen molecules. So there is oxygen in Orion Nebula itself. So like, I mean, this was observed by Herschel telescope. And so yes, they have found oxygen as well as ozone in other part of the universe. I mean, other part of our solar system, as well as other part of our galaxy itself, and extragalactic sources itself. So that means definitely, yeah, there is a chance. There is a chance that there is life somewhere else. So these are the same thing, repetition things. Like, just for clarity, I will show you, when a star collapses, like it forms a protoplanetary disk. It forms a core, hot core, and there will be a protoplanetary disk, and there will be accretion disk which is going in perpendicular to that. If you look in visible region, this region is not visible. Like, I mean, visible region if you look in the visible wavelength region, this is not visible because of dust accretion over there. But if you look in some other wavelength band, you will be able to see this. And you see that in the accretion disk, there is a lot of water as well as formaldehyde there. So there are a lot of alcohols as well as formaldehydes, all these things in the accretion disk. So this later on forms to a planet or planetesimal, and that's how there is water formation in our planets, including Earth. So complex cyanides and comet-like composition in protoplanetary disk. This is what being observed using another radio telescope, which is one of the largest in the world. It's called Atacama Large Scale Millimeter Array. This is located in Atacama Desert. This is one of the biggest telescope, biggest eye we have here on Earth. So that they have found cyanide type of molecule and cometary composition in a protoplanetary disk type environment. So that means definitely, yeah, if there is HCN, HC3N and HCH3CN there in some other protoplanetary disk type of area, definitely there will be some other complex or organic molecule. So this is the same thing which is observed in a different wavelength band in a rotational spectroscopy thing. So that's the Orion hot core, same Orion. This is high mass protostars are there. So there is also low mass as well as high mass protostars. Both have high organic complexity. And here comes to C60 and C70. So there was a recent discovery of this thing by NASA JPL. So they have found buckyballs in a young planetary nebulae. This is wavelength in microns. So the flux. So you see that there is C60, this one, as well as this is also absorption for C70. So they have found it using the same ALMA as well as IRS as well as Spitzer telescope data. They combine the data and they find it out, and they found the gaps. So ALMA is giving a lot of input. So the there are several interesting detections: H2, OH, H2O plus, C6H6, and benzene, T2CO. I mean, there are deuterium instead of, in some stars the amount of deuteriums are high. There are a lot of other chemistry as well as physics happening there. When instead of hydrogen, if there is deuterium over there, and there are stars where you even find antimatter instead of matter. So there are a lot of interesting factors which is going on. So instead of H, because the deuterium deuteriation, instead of water, you may even find D2O, like when we create the hard water. So it is actually naturally available over there. Even the common salt, NaCl, AlC, and TaO, all these things, even glycine has also glycolaldehyde, formic acid, and acetic acid has also, I mean, the vinegar, I mean, acetic acid that you use in your kitchen, even that is there in interstellar medium in high abundance. So everything is there. So this is one of the interstellar complex organic molecule spectra. So you look at the forest of lines, you can find almost everything there. I mean, except intelligent life, you find all these things over there. So yeah, I'm just skipping few slides because I think I'm already running a bit late. I already completed kind of 1 hour. So this is what I actually wanted to tell is like how the chemistry which is being happen on ice grains. So there will be a silicate or carbonaceous core. There will be simple molecules like water, carbon dioxide, methane, or methanol. When there is a cosmic ray or high energetic UV rays or some other shock waves or anything like that, that process that gives a lot of energy, the deposit energy onto this mantle, and that energy will be taken over by these simple molecules. They react together and they forms these type of complex molecules like formic acid. Here you see methanol and NH plus, I mean, and also ammonia, and there are several other byproducts of this. So say for example, CO reacts with HCO to form H2CO, and then it can again react with an H, again form CH3O and CH3OH. These type of addition, hydrogenation reactions are also being happening in the presence of energetic processing. And so interstellar dust is playing a biggest role. Like it can be a silicate or it can be a carbonaceous depending on the parent star. Some stars will be carbon rich or some stars will be silicate rich depending on the parent star, the complexity or even the channel of the reaction changes. So simple molecules again, yeah. So these are basically same thing, but they are different way. I'm just showing you the time scale when the cloud collapses, like when a proto star cloud collapses and forms this outflow plus a protoplanetary disk, and when protoplanetary disk forms actual planets and to a planetary system. This is type of the timeline, like from cloud collapse T0 for a class 2 type of star formation, 10 to the power of 7 years to 10 to the power of 8 years. That's what's the kind of timeline we are looking for. So we won't be able to do any experiment in our lab. We will only be able to, we will be only able to do some computational simulation. So this is the same slide which I showed in the beginning. So this is the life cycle of gas and dust. So the planet formation, gas cloud, it collapses, it explodes as supernovae. This is Graf Nebula, that's a supernova remnant. Then again it collapses, then it forms another stars, collapses. So there will be this the accretion disk. So like there are galaxies. So this is the life cycle. Again it collapses back. Gas will explode again. There will be a lot of gas and so it is a recycling. Basically, it's a recycling process. This is the life cycle. So these are some slides. This is the same supernova shock which I showed you earlier. This is the Crab Nebula, a supernova remnant. That's like when a star explodes, you can see this like a star exploded and its remnants is there. That's a nebulae over there. So that's basically there are a lot of these are bands of strong molecular clouds there. They are absorbing some gases as well as reflecting some gases from the star forming regions there. That's what is there. So protoplanetary disks. So yeah, this is a Hubble Deep Space Field. Look, if you look at the complete picture, except these 1 or 2 stars, rest of all the objects which is seen here are galaxies. So there are these many number of galaxies. You can see even more than this. So this is a Hubble Deep Space image, and you can understand that there are a lot of molecules even in distant galaxies. Extragalactic detections are rare, but still there are detections. So definitely there will be extragalactic clouds as well as ISM in the extragalactic clouds. So yeah, I'm just concluding this my talk because I think the time is up. So these are the basic processes. I'm just explaining you in brief. So there are basic processes: the formation of bond by radiative association. By when they're in the presence of a radiation, there will be radiative association by emitting a photon, a molecule or an ion can form an associative detachment. An electron can be detached by formation of a pair of ions or an ion and a neutral molecule. And on a grain surface, using grain surface as a platform, as I told you, when an element X comes, and with when it comes in contact with a grain plus a element Y, it forms XY, and the grain will stay back, and it can even get processed using energetic processing, and it can form a complex molecule. And destruction of bonds by photodissociation, dissociative recombination, collision dissociation, ion molecule reactions, charge transfer reaction, and neutral orbital reaction. So all these type of reactions are possible in interstellar medium. And when you make a model, so this is what I was talking from beginning. So what chemists can do is like they can go ahead and do spectroscopy. Either they can download data from online platforms and they can do process. Then if they are interested in spectroscopy, they can do that. Otherwise, if you are interested in chemical modeling, then definitely, I mean, I'm not an expert in that, but I can get you in touch with somebody who is expert in this. So you can start doing chemical networks, or else, I mean, if you already have knowledge in doing some Monte Carlo simulations or things like that, you can try doing some interstellar chemistry by putting all these chemical pathways and keep your timeline high. And only thing is like you have to give a long timeline plus less densities, and you have to keep the quantitative things. You look at some observational data, find out some previously fitted one, and you can start doing some gas phase as well as grain surface chemistry using the astrochemistry modeling. Already there are modeling softwares readily available, or else you can write your own codes. So this is actually what I did. So I'm yeah, this is just one slide. So this is like, I mean, storage ring or a synchrotron. You might have heard about cyclotrons and synchrotrons. This is one of the actual CAD diagram of one of the synchrotrons in which I worked. That is in Aarhus University in Denmark. So that's that particular source is called Astrid, and I was working in a VUV beamline. So I was building spectrographs as well as beamline end stations to do spectroscopy for astrochemist or astrophysicist. So yeah, that's what I did during my PhD time. If anybody is interested in those kind of things also, they can get in touch with me. Or else, I mean, definitely I can explain you basics of basic research stuff which is being conducted in astrochemistry, especially in molecular spectroscopy and things like that. But for chemical modeling, I won't be able to help you directly, but definitely I will be able to get you in touch with somebody who is an expert in this field. So thank you very much. I think this went a bit ahead of the time. I'm really sorry for that. I tried my very best to keep in touch. I mean, I try to keep my time, but like, I mean, it went a bit ahead of the time. So this is the ALMA, which I was talking about, Atacama Large Scale Millimeter Array. This is one of the biggest interferometric telescope, millimeter telescope, which is being installed in Atacama Desert. One of the largest one, and you can, if you go and search for ALMA, you will find ALMA a website there. You can download your own data from there. Also, they have a lot of help as well as workshop things over there. Help desk is also available, so you will be able to start working on your own if you're a beginner or if you would like to do a research in astrochemistry. So yeah, thank you very much again. If you have any questions, yeah, please. Thank you.
Hello.
Yes.
Some questions are there, I think.
Yeah, okay. Yeah, yes, please.
One question is, what are the possible advantages of cloud modeling? From Jishanitish. What are the possible advantages of cloud modeling?
Yeah, so you will be able to, there are two type of modeling things. One, as I told you, like you can do a gas-based modeling as well as a normal cloud, like I mean, dark cloud modeling. So if you are looking at gas phase modeling, then you will be you can actually basically you will be doing the chemical modeling, and you will be able to understand the chemical pathways of formation. Say for example, you have a particular molecule in your mind, or if somebody found a new molecule like C60 or a pH like coronine, or a look at, okay, take some simple things, maybe even naphthalene, just take it, and you want to find out how naphthalene formed in space. Then you can go ahead and find in literature where it has been found, what are all the physical conditions, the column density. Then you can start modeling it, like I mean, what are all the requisite formation pathways, and from there you will be able to find out the basic. Okay, so the advantage is like you will be able to find out how one particular molecule formed. Is there any subsidiary molecule which has already been there? Then an astronomer, you can predict that. You, from the computational model, you can predict, okay, in addition to this, coronine can form in this region. So if you say that by finding out from your chemical model, then an astronomer can look at that particular region and they can find out when there is a certain amount of molecule there. These other molecules, subsidiary molecules, can also be formed there. So that is, I mean, this is in research level, definitely, yeah, that is absolutely valid. People are doing that. And also the second thing is ice modeling. Like you can model an ice, like there is a dust particle, that is carbonaceous or silicon dust particle, and okay, if you model different type of, you create, okay, you can control the column density of molecules, carbon monoxide or oxygen, hydrogen, whatever, and you energetically process it with electrons or something like that, and then you will be able to come out with something.
Okay. Another question is from Shweta MB. I want to know about time travel. Is there any chemistry behind it?
Okay, so time travel until now, okay, I mean, according to my knowledge, I don't know much chemistry. I think there is no much chemistry there, because when you do time travel, this is all relativity, especially special theory of relativity. So the time dilation happens there, space and time warp is there, then mass violation is also there. Like, I mean, what happens when you travel at relativistic speed. So then it's all physics, and even physics fails at fun to explain in some areas, like so singularity. Like, I mean, you imagine about something like singularity, that's a black hole, and even the laws of physics fails there. So I don't think there is, I maybe it might be there, but I mean, according to my knowledge, we won't be precisely, that is whatever I was talking today in this talk was all quantitative. It's not qualitative stuff. Okay, it's not science fiction. It's actual science. It's spectroscopy and it's chemistry. So, like, I mean, if you are asking something like that, no, I'm really sorry, there is no such chemistry in time travel until now. Maybe in future they may find something, but until now it's not there. It's still a science fiction.
Okay. Akhil, is there any questions from YouTube?
Yeah,
Hello.
yes.
Okay. I think everything is clearly explained. Thank you, Kumar. Thank
Yeah.
you very much. We had a very good exposure into the world of molecular universe and how interdisciplinary the subject is and how slowly the reaction is taking place. We were not expecting that, how slowly the reactions are taking place there. For
Yeah,
that.
actually, I forgot to mention one thing. Like, if you look at, okay, I actually I was okay, I was supposed to explain that, but kind of because of the time limit, I couldn't. Actually, the reaction rate at very low temperature is higher than what we expect. Actually, that's what the beauty in interstellar medium. If you look at the reaction rate of reaction at low temperature, you expect it will be less, but it is not less. The reaction rate is high, but the timeline is very high. But the rate, if a column density of molecules are there, like if the a number of particles are there, definitely we can form. But we are talking about, okay, also the spatial scale we are talking is very, very high. It's in parsecs, like, I mean, like light years. All these protoplanetary disk and all these things are spread across very, very large distance. So the amount of the molecule we expect is very, very, very huge. Yeah. So
Okay, there is one more question from Nasri Palara. So, does interstellar clouds obstruct or reduce the visibility?
visibility in the sense, like, I mean, okay, if you look at very distant object, like something beyond our galaxy, like extra galactic, definitely, yeah, that's what I explained, like how we are detecting the interstellar cloud. That is by looking at stars which is behind them, like very far away stars. If you look at them, then those lights are being blocked by interstellar clouds. That's how we are finding them, right? If you look at, Beer-Lambert's law, like you have a source light, you keep something in between, the absorption will be there, you plot it against the intensity. That's how you understand how many particles are there. So this is the same thing. Like there are, okay, absolutely, the clouds are obstructing the light. That's why we are finding these absorption lines there. And from the absorption lines, we can understand the temperature there, we can understand the column density, we can understand from the Doppler effect, we will understand how fast it is moving and in which direction it is moving, whether it is expanding, whether it is collapsing, whether it is in a redshift mode, is it coming towards us or is it going away from us from the blue sheet. So all these things can be predicted just by observing the absorption lines due to the interstellar clouds. Yeah, obstruction. Yeah, that's right. Yeah.
Okay. Now I invite Dr. Drishya Arun for giving a concluding remarks and also for the formal out of time.
Hello, ma'am. Is it audible?
Yes. It's audible, Drishya.
Okay. First of all, I thank Dr. Benukumar sir for selecting the topic, Molecular Universe, Chemical Evolution and Dynamics of Interstellar Medium. So we are really unaware of the presence of organic molecules like aldehydes, alcohols, etc. in the interstellar medium. And the chemical approach towards astronomy and how to detect the molecules using spectroscopic techniques by their transitions. So I think it's a very big task to explain all these things in 1 hour. So I really thank Dr. Venukumar sir for sharing your valuable time with us to enrich us about the basic ideas of astrochemistry. Thank you very much, sir. Then I would like to express sincere gratitude to our college authorities, Principal Dr. Muhammad Ali sir, Vice Principal Professor Sufi sir, and Director Dr. Safi sir, and the IQAC Coordinator Rafiq sir for their presence in the webinar. I would also like to thank our beloved HOD, Professor Shantakumari ma'am, for her moral support and guidance. And I'm happy to express a vote of thanks to all the participants, not only from our college, but also from other colleges like teachers, students, and research scholars. Thank you very much for your cooperation. As no program can become successful with a single person, so I extend a big thanks to our staff for their support. Once again, I thank all for your cordial cooperation. And thank you very much, sir.
Thank you, Drishya. Now the link for submitting the feedback is available. All of you please submit the link for feedback. Submit the feedback with the personal details and you'll be getting the e-certificates. Thank you, sir. Akhil, I think we can conclude the webinar. Okay. We have provided the link for submitting the feedback. Okay, thank you all. Thank you very much. Thank you, Dr. Binu Kumar, for spending the valuable time for sharing with us. Thank you very much. Thank you, sir.